Okay, so now we have understood our W, which was an unwieldy form earlier. This was where we started. This was our complicated W, and we wanted to understand this. And the way we are trying to making sense of it is by saying that it is just the projection of the labels onto the subspace spanned by the feature vectors, right? So we also want to understand it in a different context and see if that can also help in a probabilistic way. And the way that we'll try to understand is using something called as maximum likelihood. So was maximum likelihood introduced at some point in the previous lectures? Yes, no? No? Okay. So let's think of this. So as I said earlier, so you have a relation between x and y, right? So you typically want a linear relationship, but then there is some noise associated with it, right? And you don't want to fit the noise. If you fit the noise, then you are getting a complicated model, and you want to avoid that. That is the goal, right? So the one way to think of it as, right? So this red line is your mx plus c, right? So your standard y equal to mx plus c, which can be written as y like this. But what we want to do is think of your y as actually somebody giving you y in the following form, right? He takes an x, he finds out w transpose x for a w that he wouldn't show to you, right? So that is hidden from you. So he computes w transpose x, and then he adds a noise to it, and that noise is what I call as epsilon, right? So the noise comes from a normal distribution with mean 0 and variance 1. So normal distribution, I think, was introduced in one of the probability lectures earlier, I am assuming. So basically, this is what is called as a what people call as a generative view of data. Right? Earlier, we did not assume anything about how our x's and y's were given to us. Now we are making an assumption, explicit assumption as to how our x and y are given to us. And the way that we are saying is, somebody took an x and then computed w transpose x using some w unknown to us, and then added a particular noise of a particular form, right? And now gave y to us, right? So this is what is given to us now, right? So now again we have this x1 y1 till xm ym, which is given to us, and we know that it is generated on this form. We know the exact statistics of the noise as well. In this case, it's a Gaussian noise, right? So now we want to find out the best W. So the natural thing to do is to find that W which might have most likely generated this data that we have. Correct? So when I say most likely, when I use the word likely, it means implicitly there is some randomness that I am assuming about the underlying process that has generated the data, and that randomness is exactly the way that noise is added. Right? So which means the way that we will formalize this is by saying that given a data set xi yi from I equal to 1 to m, and you are asking the question, what is the chance that this data set could have been generated using this particular w, right? So any w, right? So if I just call this w as some vector w, right? For any vector w, what is the chance that this could have been generated, this data set could have come using this w? I can talk about chance because I am assuming a generative model for data, right? So there is a probability involved. Now what is the probability that if I had used w, I would see this data? That is the question I am asking, right? So and that can be computed in the particular case of Gaussian distribution. For this case is what is the mean of y, right? So what would be the expected value of y? Can someone say if y is generated as w transpose x plus epsilon, where epsilon is Gaussian noise, what would be the expected value of y? So what is y? Y is w transpose x plus epsilon. What is w transpose x? Is something random about w transpose x? There is nothing random about w transpose x. So there is no expectation or anything for that. So it is just w transpose x plus expectation of the noise, right? What is the expectation of the noise? What would you expect for the noise? Why is it 0? It is because of the way that we have assumed about the noise, right? So this is 0. So the expectation of y is then w transpose x, right? Which means the mean, on an average, you are expecting to see w transpose x, which is on that red line that we saw earlier, but then with some noise added to it, and that noise statistics is given by this. Now which W is the question, right? So now you want to find that W. We'll ask the reverse question. If I fix a W, what is the chance that I'm going to see this data set, right? So, and that is given by this, right? So now I'm assuming all the data points are independent of each other. So which means the probability that I see x1, y1, comma x2, y2 is just the probability of x1, y1 times probability of x2, y2. Why can I write this? Because I'm assuming they're independent of each other, right? So the probability, the fact that I'm seeing x1, y1 gives me no information about the fact that I'm seeing x2, y2, right? So that's why I can write this as product P of A intersection B is P of A into P of B, right? So that's independence, and it follows. So now what is this probability, right? So probability of seeing x1, y1 is given a particular W is this, right? So is a Gaussian distribution with mean W transpose X, and hence we can multiply all the probabilities to see that the probability that we will see this data set with a fixed W is proportional to this term here, right? So now this term, so now we want to find that W. What is the W that we are after? Are we after the W that minimizes this or maximizes this? So what is this? This is the chance that you will see this data if the true W was this W. Do you want to increase the chance of seeing this data or decrease the chance of seeing this data? You want to increase the chance. You want to maximize the chance of seeing the data. You want to find that W that maximizes the chance of seeing this data, right? So that is, so you want to find the maximum likelihood estimate for W. That's what it is called, right? So, and one simple thing that people do is you take the logarithm of your likelihood function, which does not change the W. Like how you added the 1 by 2, it did not change the W. Similarly, you can take a logarithm and it does not change because log is like a monotonic function and so on. So let's leave it at that. But if you take the logarithm of this, you end up with something like this, right? And does this look familiar to something that we have seen earlier? This is exactly the cost function that we saw when we started off by trying to minimize, right? With the only difference being there is a negative sign. So why is that? Why is there a negative sign? Why is there a negative sign here whereas there was no negative sign earlier? Exactly, right? So here we are trying to maximize the chance, whereas there we were trying to minimize the noise, right? Minimize the error, right? So which means what essentially we have tried to say is maximizing the log likelihood is equivalent to minimizing the linear regression's least squares loss, right? So now we have tried to understand the same problem in two different ways, right? So one is you set it up as a cost minimization problem, and then you did a derivative, and then you ended up with a W, right? And that W we tried to interpret it as what was the geometric interpretation of W, which came out to be as projecting your target vector onto the space of subspace spanned by the features. That was one interpretation. Now here we are saying that it is not just that. If you used a noise model like this, then maximizing the log likelihood is equivalent to minimizing the function that we start off with. So now one question is, how critical is this assumption that the noise is Gaussian? So if I were to change this noise model, what would happen? Where would this affect in this set of equations? Where is this assumption of normal or Gaussian noise is coming into the equation? Any thoughts of that? So why, when I wrote e to the minus yi minus w transpose xi squared, I mean, what does that mean? Why should it be e to the minus yi minus xi w? It could be anything, right? So why did I write this? It's a normal, so it's the PDF of a normal distribution, right? So the noise is actually directly affecting the likelihood function, right? So if I'm going to change my noise model, my likelihood function is going to change, which means I will be entirely maximizing something else. So it is this noise, this log likelihood, which is a normal log likelihood, is key here, right? So we cannot arbitrarily say, we are not saying that maximum likelihood is equivalent to linear regression. We are saying that maximum likelihood with a normal or Gaussian noise is equivalent to minimizing the linear regression problem. Right? So that is important. So you can play around with trying to see if I change this noise in one of your lab, in today's lab session, you will also see if I change the noise, how is this affecting the whole problem itself? Would we still be getting the same kind of answers and so on? Right? So that is something that we'll look at in the lab section later. Okay. So yeah, so one of the things is, so we looked at this linear function, linear regression, which was like fitting a line, right? But clearly not all data is linear, right? So you cannot expect data to be linear always. So let's say the data was like this, right? So now it probably is better to fit some other nicer curve than a linear model in this case, right? So of course you don't know which is the best model choice to make. But let's say if your data was like this, you would not really fit a linear model to this. You would fit something else, right? So you want, in some cases, you do want non-linear fits to data. But then we don't want to lose the power and simplicity of a linear regression model, because we know that it has an analytical solution. We know it has a nice geometric view. We know it has a good generative model view in terms of maximum likelihood and so on, right? So the one way to partially fix this is to use what are called as basis functions, right? So basically what you do is you still work with a linear model, but you map your input to a nonlinear space. You map your input to a different space, and in the mapped space you work in a linear model, right? So these are called as basis functions. So instead of using your features as such, you transform your features to something else, right? For example, your feature could be x1, x2, and you can map this feature to something like 1, x1, x2, x1 squared, x2 squared, x1, x2, right? So now a linear model in this case would look like what? So your h of x is going to be w1 plus w2, or let's call it w0 plus w1 x1 plus w2 x2 plus w3 x1 squared, and so on, right? w4, let me write it down, w4 x1 x2 plus w5 x2 squared, right? So it's still linear, right? It's linear in the parameter space that you're trying to learn. You're trying to learn a linear w, but then you have mapped your data to a higher dimensional space, and you're trying to learn a linear model there, right? So in that sense, it's still a linear fit to the data. So you'll also play around with some of these linear functions in your lab session today. So I won't say much more about this at this point. Here is one point. So this was a geometric view, and what we ended up with was this way to calculate our w, right? So so let's say, so we saw that this was a matrix, right? So this was a matrix, and this was the pseudo inverse, which was inverting a matrix. And inverting a matrix is typically a very, very hard problem. Right? Hard problem in the sense it takes cubic time, or it takes, I mean, if your dimension of the matrix is something like d cross d, then you're going to end up with something more than d squared time to something. I mean, the best possible, I think, is d to the 2.6 or something. Typically it's d cubed to invert a matrix, which is hard, right? So when d is like 1 million, you will end up spending a lot of time to invert this matrix, right? So which is not a good idea at all. Though we have a nice closed form solution, computing this for large problems is a tough problem, right? So how do we deal with this? One way to deal with this is what we call, I mean, what we want is, you want an iterative solution, which means you start off with some w as a guess to your answer, and then move one step at a time so that you go closer and closer to the actual w that you want. So these are iterative schemes, right, for linear regression. So what I will do, I mean, I wanted to do this, probably I'll do it in the next time. So basically, how many of you are aware of gradient descent algorithm? Can you raise your hands up? Well, okay. So many of you, but then some of you are not. So what I'll do this the next time, and see why this is a very, very powerful fundamental optimization method, and give some insights into how this can be used to solve the problem, iterative way of finding out w as well. right? So probably at this point I will stop today's class. And are there any questions? Okay, thanks.